Hello and welcome to my video where I will discuss mixture of experts and how they're used in transformers to improve computation with the same memory requirements. So first of all, we need to understand where mixture of expert models are used. And as the name suggests, it's many experts which do a specialized role of something that was a jack of all trades. And in this case, it's the pointwise fully connected feed-forward neural network, which you can see here, which has the mixture of expert model. So in this great example, we can see that we have more parameters being passed into our transformer block. It goes through self-attention, and then there's the layer norm plus the skip connection or the residual stream. And then we have a router or a gating network, which decides which of the four feed-forward neural networks here that we have in this example are best suited to evaluate this token. And in conventional settings, these four feed-forward neural networks would have 1/4 of the parameters that an entire network would have, so that you can maintain the memory consistency while adding more specialization. And in this case, we can see that the router gives 0.65 probability to the second one for the token more, and therefore that's what's used here. And then there's an 80% probability for feed-forward number one, and that's what we go through here. So this router mechanism is a learnable parameter which will give the probabilities over softmax of which of the experts to use. And in this example, we can see that it's called hard routing or top one routing, which means that we only pick one expert. But as you'll see in particular with DeepSeek mixture of experts, it's much more diverse and combinatoric than simply picking one expert. And the traditional mixture of experts schemes use a weighted average to combine all experts. So I'll show you how this works. Of course, this example, as I said, is only using one feed-forward network to go and propagate more through the second one and parameters the first one. And then we would do this recursively, or not recursively, but in the consecutive blocks. But as you can see here, we have a weighted average in the standard mixture of expert formulation. So what do we have here? G is the gating function. So this is a probability distribution, and F is the function itself. So this can be thought of in the context of the transformer as the feed-forward neural network. So what this means is that the router or the gating network, same thing, you can think of it as a triage nurse in a hospital. So that means that when somebody comes to the emergency room, the triage nurse is the person who says, okay, this person had a heart attack, send them to the cardiologist. This person broke their bone, send them to the orthopedic surgeon, etc. And this will give the relative weights. So if we have somebody who had a heart attack, then the gating function, and let's say that there's an orthopedic surgeon and the cardiologist, the gating function might say, okay, we'll send 90% of the weight to the cardiologist for the heart attack person and 10% of the weight to the orthopedic surgeon. And then that means that we'll weight the feed-forward neural network for the cardiac surgeon by 90% and then 10% for the orthopedic surgeon one. So in this case, it would be a simple sum of 0.9 times cardiologist plus 0.1 times the orthopedic surgeon. So you can see that this formula, although it seems kind of strange, I don't know, I don't like to see abstract variables. When you have an example, it is very simple to understand. And as I said, the gating network is a probability distribution. So if you sum up all of the different values of the weights, then you'll get one. So I'm going to use the previous example again. That's to say we have 90%, so 0.9 for I equals 0, which would be the cardiologist. And for I equals 1, we have 10% for the orthopedic surgeon. 0.9 plus 0.1 is equal to 1. So that's probability distribution. Furthermore, as I said, it's learned. So what you can see here is that it's a softmax function. So the value for g of I is exponential of this linear combination of of w and x. And this is extremely important to note. What is x? X is the token itself. So if I come back here, just remember that more is x1 and parameters is x2. So let's come back to our example now. That is to say that with our learned gating weights, wi, so there's wi for the cardiologist and w0 for the cardiologist and w1 for the orthopedic surgeon, we'll multiply each of these with the token x, which could be more, but let's say that token x is a heart attack patient. So this dot product with the cardiologist weight, W0, will be very high. And then this softmax will give 0.9. And if we sum it over both the cardiologist and the orthopedic surgeon, and then we do the same thing for the orthopedic surgeon, and then this will give the weighting of 0.1. So once again, this sum here is in fact for each term, the exponential of the learned weight and the token itself. And then if you do this sum, which is right here, with the same thing on top, then you'll get numerator divided by denominator, which are both equal, and that gives 1. So this is quite interesting to see. Of course, we have the probability distribution equal to 1 here. And then if you want to determine the probability for a specific token, use a softmax with the learned weights for each gating network, which, as I said, it corresponds to a doctor in my example, but in real life, it will correspond to one of the expert feed-forward neural networks that are once again supposed to be specialized versus a jack-of-all-trades feed-forward neural network that is not as sample efficient. So I said once again that traditional mixture of expert models are weighted sums over the entire network. However, in transformers and in all of the flagship models, we use a sparse activation. So you can see in this diagram, we have g prime of E1 is x equals this, and g prime of E2 is this. And what this means is that we'll only take the top two feed-forward neural networks, which is to say that after the first two highest probability in the softmax, we cut everything off. So let's say that now we add a third doctor into our example, who is a pediatrician. So we have now, let's say 0.88 for the cardiologist, 0.1, so let's keep it the same, and then 0.2. So 88%, 1%, and 2%. So we completely discard the pediatrician. And now instead of doing 90% and 10%, because the pediatrician took some of the weight from the cardiologist, now it'll be more like, 89% and 11%, because we're doing 0.88 divided by 0.88 plus 0.2, so 0.88 divided by 0.9. And then here we have 0.2 divided by 0.88 plus, it's the same denominator. So all I'm trying to say here is that in the models that we use, it doesn't make sense to split up into experts and then use all of the experts, because the whole idea is to use less memory. Because as I'll talk later, when we're doing inference and we have all of these experts, if we only activate 2 out of the 10 experts, then we're only using 20% of the memory in our VRAM, which will reduce computation by the proportional amount that you have of experts. And this is why that we pick sparse activation instead of the classic weighted average in order to take advantage of this memory exploitation. And once we have our weighting values for the top two, then we of course calculate our Y. So I just love this first example here. So in this instance, let's assume that we go to 2 and 3. So there's one error to 2 and one error to 3. This would be top 2 routing. If there's 3, top 3 routing, of course. So I don't know why there's balloons, so ignore that. And therefore, we would have whatever the probability, whatever the gating percentage is for network 2, multiplied by its output, and whatever the gating weight is for network 3, multiplied by network 3's output. That's to say the output of the feed-forward neural network. So I know it says 1 here and 2, but I hope you could follow my example nevertheless. But if you didn't, then don't worry, because I have another example. So I'll just quickly move my camera 1 second so you can see on the left we have expert, and then on the right we have raw score. So first of all, let's verify, are the raw scores a probability distribution? And yes, it is, because 0.6 plus 0.3 plus 0.1 is 1. And this gives a relative weighting. This is a courtesy of ChatGPT if you haven't noticed already. And the model selects E1 and E2 as the top 2 experts because we're doing top 2 routing. But now we need to normalize the weights because we have discarded E3. So we normalize G prime of the first expert and G prime of the second expert to get 2/3 and 1/3. And then now, as we have the formula, which I've evoked here, it's 67% of the first expert's weights, or rather output, and a 33% weighted output of the second expert. So I hope this gives you an intuitive grasp of what we're trying to accomplish with mixture of experts, which is to say we want to weight the experts based on the learned weights, which the learned weights themselves determine the appropriateness. So I didn't mention this explicitly, but when we have this example here, and we have our WIs that are learned, so we apply this linear combination to determine the weighting factor, this would be based on the semantics. So maybe parameters would be fired best with the first network, because let's hypothesize that the first network is a machine learning expert. So the machine learning network here, FFN1, will have a much bigger relationship with the parameters token that it has learned. So we do the learned vector W with the parameters token, then these other two. So these other three. So maybe this one is a art expert, this one is a science, and this one's chemistry. So the machine learning one will have a higher dot product, and through the softmax give a better probability. And this is how we choose which expert to pick. And before I talk about DeepSeek, I want to talk about the model which really put mixture of experts in the limelight. And this is Mixtral 8x7b. So in this model, there are 8 fully connected feed-forward neural networks, which have 7 billion parameters, so that with top 2K routing, which is what's used in the algorithm, we only use 14 billion parameters at inference because we only pick 2 feed-forward neural networks. So 2 times 7 is 14 billion, or 2 times 7 billion is 14 billion, instead of using all 56 billion of the 8 models. And I said 56 billion erroneously or incorrectly because in fact, it's only 47 billion, but you may be asking, okay, 7 times 8, that's 56. So if you use all 8, it has to be 56. But here's the thing. When you have a feed-forward neural network, there's many efficiencies happening. And one of them is that there's shared parameters across the networks. So we can share parameters to reduce by 9 million the number. So it goes from 56 to 47 when you share the parameters across 8 networks. But still, 14 is much better than 47. And this demonstrates the improving computation round. And once again, even though a sparse mixture of experts model, so sparse meaning it doesn't pick all the experts, it avoids using all parameters at inference, it still needs to load them into VRAM on the GPU because it needs to have all the experts to choose from, but then only pick the ones which were weighted by the gating network. So it does not improve memory bound in terms of VRAM because you still need to store them all on the GPU. But instead, we increase the model capacity while maintaining the same amount of computation, which is to say, if you compare Mixtral 8x7b with an equivalent dense model, so I didn't mention this, but we have a sparse model, which uses a mixture of experts, and a canonical model would be called a dense model, which means that all of the parameters in the feed-forward neural network are used at inference. So dense and sparse being mixture of experts, dense being the classics. So what Mixtral 8x7b can do is be equivalent to a 56 or 47 billion-ish parameter model, even though it only has 14 billion parameters used at inference, because when we pick a specific model, we have improved sample efficiency through this specialization. And one thing worth noting is that mixture of experts is best applied in sparse environments because we don't want the experts to have overlapping knowledge. So if you think of a environment or some type of formulation where it's very uniform in terms of the knowledge, then you just need one expert, which is to say a standard model. But if you look at language, boy, is language sparse. Like there's some words that you only say once a year. And this means that certain experts can specialize on very specific parts of language. And it really is tailor-made, you can say, for language. But let's not think of the positives only. I'll evoke this when we talk about DeepSeek in particular, but just to get started with the weaknesses of a mixture of experts, something that can happen is that we focus on one expert in particular, and this is called a load imbalance since one expert is being chosen much more than another. And Noam Shazir, who pioneered the transformer right here as a part of Attention is All You Need, has proposed 2 different techniques which are no longer really used in their implementation at the time, in part because of DeepSeek mixture of experts, which has improved all of these facets. But in order to make sure that all the experts are used appropriately and in the same approximate amount, you can do something called random routing or noisy gating. These mean the same thing. And this means that if you're doing top K routing, let's pick the first expert greedily, so 0.6. But then if you see 0.3 and 0.1, let's put a probability distribution over that. So in this case, with 75% probability, we pick expert 2, and with 25% probability, we pick expert 3. So adding this stochasticity will ensure that some models or some experts which may not be picked in a specific situation which will balance them out. And lastly, there's something called expert capacity. So right here, we see that in this case, more is evaluated by FFN2 and parameters is evaluated by FFN1. And if we have a context window of 1024, let's say that each expert, if there's only 4, can at max handle 512 tokens. This means that once FFN2 has handled its 512th token, we just cut it off and we become a 3 expert model. And what this means is that it cannot do more than the majority. So if we have 1024 in our context window once again, then let's just set it at 511, I guess, so that it will always do less than 50%, which means that the load will be balanced more equally across experts. Okay, so now that we have a common foundation on mixture of expert models, let's talk about DeepSeekMOE. So there's 2 research questions that we can postulate to think of how DeepSeek developed their mixture of expert strategy. The first one is, what if we have more experts, each having fewer dimensions? That is to say, why stop at 8 experts? Why don't we just go a lot more. This wasn't the idea novel to DeepSeek, but they have a very unique way of interpreting this. And then also, the second research question is, how can we reduce knowledge dominance and redundancy among experts? So in the second research question, I just mentioned two concepts. So knowledge redundancy and knowledge dominance / knowledge hybridity. These are the same things. And let me explain their definition according to DeepSeek. So knowledge redundancy is when we have some tokens that require common knowledge leading to overlap between experts. So maybe it's the concept of being nice is good. And each model should know this. So there's redundant information between the experts, and this kind of defeats the purpose because we want the experts to be specialized. So this is called knowledge redundancy. And then knowledge hybridity or knowledge dominance is that since there is only 8 experts or 4 experts, so not that many, none of them are truly specialized, because if you're 1/4 of the model, then you need to know 1/4 of the world, which is still a lot. So once again, these are the two research questions. Just let's make more experts, and then how do we solve redundancy and hybridity or dominance? So DeepSeek MOE comes up with 2 novel ideas. The first one is fine-grained expert segmentation for a combinatoric increase of experts. This makes me really excited. Like, I can't contain the ingenuity in how they developed this. And secondly, there's shared expert isolation, which means that we make one expert consolidate the information about the common world model such that the other experts have an improved parameter efficiency since they're no longer redundant. So what I mean by this is that, as you can see right here, there is one expert which is always routed, which means that it's shared, and therefore these other experts can focus on specializing themselves instead of having to know all of the redundant and menial things about the world. And in this example, you can see we have the conventional top 2 routing, which I already mentioned. Then there's the fine-grained expert isolation, which is the first improvement in DeepSeek MOE. And the second improvement, once again, is adding this shared expert. So now that we have a shared expert, we need to give a name to the other experts. And the name given here is called a routed expert, because the router only assigns to the routed experts, as the name indicates, and the shared expert is deterministically always chosen. And to come back to fine-grained expert segmentation, what we're doing here is that we're dividing each expert into m pieces, so that there's m more experts. So if we have 8, then we'll divide each into 4 if m is equals to 4, and now we have 32 experts. So you can see this is not sophisticated mathematics. We're just quadrupling, making 5 times, sextupling. Either way, it produces similar effects, but this is all hyperparameter, of course. And the overall effect is that we have a richer representation capacity thanks to the combinatoric increase of models, and it gives the same parameters used very importantly, because if we increase by 4 the number of experts, then we'll reduce by 4 the parameters per expert. And this allows us to have more specialization since we have more experts. So if you can think of, let's say, the Nobel Prize, instead of having science, chemistry, and biology, I'm just making this stuff up, what if we had a Nobel Prize for molecular biology, cellular biology, and this gives us a more fine-tuned way of awarding the prizes. So for example, Jeff Hinton doesn't steal the Nobel Prize in physics because he's not even a physicist. So that's our hot take of the day. And once again, with respect to the shared experts, they handle the fundamentals, and then they can leave the esoteric information to the routed experts. So I talked about a combinatoric increase in the combinations of experts. But what am I talking about in particular? So let's see what the numbers are. So let's consider that we have a transformer with a feed-forward neural network that quadruples the size of the residual stream from 1024 to 4096. So it does an up projection to 4x and then down projection to 4x. So it just performs the computation on the residual stream. And if we use our classic mixed role of experts 8 times 70 model, we have top 2 routing with 8 experts. And this means that we have 8 choices and we choose 2. And 8 choose 2 is 28, okay? However, let's instead split each expert into 8 pieces. And if we split 8 into 8, that gives us 64, so 8 times 8. And we're of course going to then reduce by 8 so that in fact 1024 becomes 512. So once again, we have 1024 becoming 4096 in the standard model, so it's times 4. But now that we've multiplied by 8 here, we divide by 8 here. And this is once again because we want to keep the number of parameters per expert equivalent. And I'm about to tell you something that will shock you. I promise you. Because 64 choose 8, which is the number of choice that we have. Can you guess in what order of magnitude it'll be? Maybe in the order of millions, maybe in the order of billions? Wrong. It's 489 trillion approximately. So we've gone from 28 to 489 trillion expert combinations by increasing the number of experts by 8 and reducing the size of the pointwise fully connected feed-forward neural network by 8 to 512. And this is literally free lunch. I know they talk about the free lunch theorem, but they're wrong. This is the definition of free lunch. And once again, the total activated number of experts remains the same. So not only does the number of parameters per expert remain the same, but when we activate 2 experts, we get 2 times 4,096, so 8,192, and 16 times 412, 8,192. This is mind-blowing stuff, and it's so simple. So this is why you shouldn't think that there's some very obscure mathematics happening in these models. That is sometimes the case, but sometimes we're lucky and it isn't. So now that we've discussed shared experts and fine-grained expert segmentation, the 2 breakthroughs in DeepSeekMOE, let's go through the DeepSeek progression once more. So we had top 2 routing with n. So that means of the, let's say n equals 64 nodes, we pick 2, and then we move on to the fine-grained experts. So our m, which is the key here, is 2, because we know that we go from 2 to 4, so we multiply by 2, and also we can see the 2n right there. So we would have 120 experts now, and pick from 4 of those to get our output at every time step. So that is the fine-grained expert, but we add one more, of course, the shared expert addition, and in this case, k in the router is reduced. So this means that now one shared expert is always chosen, and then the 3 other specialized experts go through the router, and the formula for getting the number of routed experts would just be our original k value multiplied by m minus the number of shared experts. In this case, 2 times 2 minus 1 equals 3. And you may be wondering how DeepSeekMOE is implemented in real life. So in the paper's implementation, there's 64 experts with 2 shared experts being chosen at every time step and 6 routed experts for a total of 8 experts per time step, or 1/8 of the 64. So this is the implementation in real life. But for our toy example, we only have 1 shared expert and 3 routed experts. And I mentioned load balancing earlier on. And how does DeepSeekMOE address the problems of load balancing? First of all, experts are distributed across GPUs to avoid any bottlenecks, which can precipitate imbalanced experts. And we also change the loss. So I mentioned Noam Shazir's loss, which was the noisy routing and the expert capacity, but we have different losses here. So there's something called expert level balance loss and device level balance loss. So expert level balance loss, you can think of as somewhat similar to expert capacity, which is to say that we won't favor one expert over another too much. And then device level balance loss means that on each device, we have a certain number of experts, and we won't privilege a specific device. And this is just a computational thing, because if you only use one device out of all of them, then what's the point? Just have one device instead of parallelizing. And if you don't like math, you can click away from the video now, but I did save the most difficult part for the last. So this tells you how we can calculate the output of a feed-forward neural network with the mixture of experts shared and fine-grained method using DeepSeek. So this is the first part, which is much easier. These are all the shared experts. So you can see here, first of all, this is the output hidden vector from the T token at the elf layer. So honestly, just ignore these indices. I don't really pay attention to them because we just want the large picture. So we sum up over all of the S experts, and we pass it through the feed-forward network. Feed-forward neural network, this is just standard protocol because the shared experts always are activated. If you remember here, we don't have a router for the shared experts because the router doesn't have the right to say no. The shared experts always get their way. And now let's look at the more difficult part. So MN is the total number of experts, and we sum from the first routed expert. So we do K of S plus 1 to avoid that K of S. So from the first expert all the way up to MN. And then within the summation, we have what you remember from much earlier, which is our gating function, which gives us the weights over the experts. So let's just verify here. And you can see that we have a specific rule for if we're getting it or not. And you've seen this before, so don't make this foreign to yourself. All this is saying is that if it's in the top K, then we will apply the weight. And if it's in the top or outside the top K, then we won't. So if you guys remember when we discussed this example, these two were in the top K, so they were themselves. And then this one, since it was outside, and this one, I mean, it's already 0, so it doesn't matter. But E3 becomes 0 because it was outside the top K. And that's exactly what we have written here. So once we have this, we'll multiply this by the output of each feed-forward neural network. But this is to say that if an expert is not evaluated, in this instance, we would multiply by 0, but that's a wasted calculation. So in the implementation, we literally only call the networks which have been chosen via this softmax computation. So once we have the weighting chosen, whether or not it's in the top K, it's simply the softmax between the output of the attention mechanism at the specific layer, and EI, which is the learned weight for each routing expert. So now we've gone through everything. So once again, our output is equal to the shared experts plus the chosen routed experts, which we only choose as the top MK. So once again, I think I said K by mistake, but everything within the framework of the fine-grained experts is M times whatever the original value was. So we're just multiplying everything by M. So we have this combinatoric increase. And then we also add the input of the residual stream because we have the skip connection. So we always add whatever the input was to the output, and we have our shared fine-grained experts in this summation. This gives us the hidden vector output for the teeth token at the elf layer. Voila. Okay, let's just get back to this image because that's how I want to close off the video. And I'm just going to give you the too long didn't read. I probably should have done this at the start, but if you're still here, I want to give you the important information that you should remember if you forget everything else. And that is that inference is faster using MOE than a dense model with the same number of total parameters. So I'm not saying activated parameters, I'm saying total parameters. So a $56 billion parameter dense model will be much slower at inference than a 56 billion total parameter, but only 14 billion active in a mixture of experts setting, because you just simply have less weight to compute in the forward pass. Secondly, mixture of expert models pre-train much faster than dense models. And why is this the case? It's because of the sample efficiency. So I mentioned sample efficiency because when you have somebody that's specialized, they'll perform better. This is just a fact of life. If you train somebody to do everything in the factory, or you train one person to do every task, which one will be more efficient? Of course, it's one where everybody's trained to their specific task. So in a training run, when you're going and performing teacher forcing, which is to say, giving your model auto-regressively the context and then asking them to perform the next token prediction, well, when you do the forward pass to get your gradients, then you only use the portion of inference. So that is to say, the fraction of experts that you choose. So you'll just do pre-training much faster as well. And this is once again tied to sample efficiency because we're only using a portion of our total feed-forward neural network capacity. However, there's always a however. And this is the fact that we're trading performance for complexity. And this is because we're adding more experts. It's becoming more convoluted, but we do have some performance increase. The mixture of expert model and DeepSeek was better than models which had many more parameters because of this expert specialization. And not only is it more complex, but fine-tuning sucks because it leads to overfitting due to the difficulty to generalize. So the issue is when you specialize, well, it affects generalization. So of course, if we come back to the factory, every person in the factory knows their task and they're very good together. But if one of them is sick, then you specialize. And even though everybody knows how to do their task perfectly, you miss one person and everything's screwed. Whereas if you train one person to do everything, they'll be really bad, but at least they can do the job. So once again, you got overfitting due to this generalization difficulty. And that's why fine-tuning is not fun. But unless you're a fine-tuning machine learning engineer, then you don't need to worry about that. And last but not least, I'm going to discuss the hyperparameters before I let you go. So for DeepSeek MOE 16 billion, we have 28 transformer layers with a hidden dimension of 2048. They use multi-head attention. This is changed now because they use multi-head latent attention in the current DeepSeek pipeline. So V3, for example, and V2. So anyways, they use 16 attention heads with each attention head being 1028. That should be 2048 divided by 16. And they just initialize everything with a standard deviation of 0.006. That's quite a eclectic choice. And we substitute all FFNs for the model with the MOE layers except for the first layer. And this is because it has been empirically shown that the first layer of many transformer models is almost an extension of the embedding. So if you remove or if you play too much with the first layer, then your embedding will be screwed up and the model will be kind of communicating in a language that doesn't really understand. So we don't touch the first layer, but then after that, we add all of our mixed expert layers. And now we can get to the real implementation. So we have two shared experts here. So we only have one here, but we have two in the paper. So add one more. And there's 64 routed experts where each expert is a quarter of the size of the standard feed-forward neural network. Furthermore, each token is routed from 2 shared experts and 6 of the 64 routed experts. So in this case, it would be 64 choose 6, but I can still guarantee you that 64 choose 6 is a unbelievably big number. And even finer expert segmentation is not used due to the reduction in computational efficiency with very small expert sizes. So that means that 64 is already pretty good. They didn't make it like 128 or whatever it may be, because you can't just keep on scaling. There's a certain point where the complexity performance trade-off is lost. But they say that when you have 16 billion parameters, you can still do finer granularity. And this just goes to show the power of the bitter lesson by Richard Sutton. And one thing that I will leave you off with today is that the 16 billion parameter model only has approximately 3 billion parameters. So they don't reveal the calculation, and I didn't put the effort to go and count the individual parameters to see how they reduce this, but it goes to show that since we only use 6 out of 64, which is kind of like 1/8, a bit less, of the number of experts, then this is kind of like 1/8, because if you divide 16 by 8, then you get 2, and we'll add plus or minus 1 billion for our rounding error, and there you go. We have our activated parameter size, which is used at inference, which greatly reduces the amount of computation needed, but you still need the VRAM. So that was the video. I hope you have an excellent day, and thanks for watching.